Hi friend, welcome to A Water Connection, a space created to learn, connect, and multiply the power of a conversation to give visibility to the water industry. I'm Jess Borges, a passionate human who believes you should increase your water curiosity. Welcome to this new episode. Today, I'm virtually sitting with Sally Williamson, who is going to help me and help us understanding what is water treatment. Sally has worked in a range of areas in the water industry for more than 20 years, from microbiological analysis in laboratories through to treatment plant design, optimization, and commissioning. Sally's passion is water quality and risk management, particularly for drinking and recycled water systems. She currently works ensuring sustainability, reliability, and resilience for Sydney Water's drinking water treatment systems in our changing climate, which is very interesting. And she's also the co-chair of the Australian Water Association Water Quality Specialist Network. So we're very lucky to have her today. Welcome to our Water Connection, Sally.
Thank you. Thanks for having me.
Sally, as I just mentioned briefly, you have extensive experience in everything related to water treatment. But for someone who may not be that familiar with this area, why do we need to treat water in the first place?
Good question. Well, obviously, many people see water as just something you turn the tap on, right? It comes out, we can drink it, it's fine. Many people even don't drink water from the tap, which is, another question for another day, another issue. But essentially, we get our drinking water from the environment. The environment, is subject, and as you mentioned before, we have this changing climate. So we see a lot of variation in what's happening in the catchments, in the drinking water catchments. So therefore, we might have days where the water is really clean and it doesn't need a lot of treating. In fact, you'll see some schemes around Australia where they only need to disinfect because the catchments are so well protected and they don't have that kind of variability. But others, like say if you have water that is coming from a river, which can change quite rapidly in its quality, or if you've had potentially, say, a bushfire in your catchment or a drought followed by some extreme rain event, you can get some really widely variable water quality in your raw water. And that water is not safe to drink without it first going through your water treatment process. So essentially the water treatment process is there to meet a set of water quality objectives. In Australia, we have our Australian Drinking Water Guidelines, which sets out a set of limits that are based either on health-related targets or aesthetics. So if it's smelly or if it's a weird colour, we don't like that in our drinking water. But I mean, it's not unhealthy. It won't kill you. But obviously, we want drinking water that people will actually drink. So the drinking water process is there to take our raw water to that water quality objective. So it's meeting those guidelines when it comes out of the tap, when you turn it on, essentially.
Yeah, excellent. I mean, I think you mentioned it there, like the process, and you mentioned that sometimes only disinfection is necessary. So what other processes are necessary then when it's really like not really good quality? What are the things that we need to do to water to get it to that standard and to that kind of objectives that we want to have?
So depending on what sort of water quality you have, there's different typical treatment trains that you would see. So I guess the most basic is just disinfecting. That's when you've got really low, say, solids, low colour. It's really sort of pristine quality water. You just need to disinfect. The next step up is that you would have filters. So those filters would take out the solids, your pathogens. You'd always have disinfection on the end, but it's those solids that do the hard work. And then as part of that filtration process, you'd have an element of chemical conditioning at the front end of the plant. So it's quite a complex process, the chemical part of it. And if you're a chemistry nerd, then right up your alley. I'm a microbiology nerd, so I'm not. I won't try and decipher it, but it's your coagulation, your flocculation process, which the idea behind that is to create from the contaminants in your raw water solids, chunky solids that are big enough for the filters to capture. So once you've gone through the filter, you've only got essentially the very, very tiny things that the filters would not be able to capture. There's many types of filters you would see. So typically you'll see sort of sand, like dual media sand anthracite filters. That's what you would see at many sort of conventional treatment plants. But these days we see, say, membranes, so your microfiltration, ultrafiltration, not so much your reverse osmosis. That's in the advanced sort of area, which we won't get into today. We can leave that one for another time if you like. But then there's also, if the raw water is dirtier again, you would add sort of a pre-treatment phase, which is typically a settling phase or potentially a flotation phase. Or it's both come under the umbrella of sedimentation, I suppose. So the purpose behind that, again, is you've got solids coming in, they settle, you get the nice cleaner water off the top. That then goes through your filters and the disinfection. Or if you have, say, an algae risk in your raw water, you would probably select a flotation type of process, which instead of going down, the solids or the algal particles go up and you get your nice clean water from the bottom. So they're the kind of conventional treatment processes that you would see typically. There are variations of those. There's, other processes you might see if you have other types, or really, say groundwater. If you're sourcing your water from groundwater, you might have might be very sort of hard water. So you might do some, say, aeration, which is essentially just putting the water or aerating the water or running it over some kind of framework that allows air to get in, and that removes, that helps to remove some of the. This is where my chemistry fails me.
Remove the hard part of the water. Would that be kind of the idea? If it is hard, then we go through that aeration process. It sounds like it's a very modular kind of water treatment. Like you mentioned, like pre-treatment and all the different processes, but it certainly is kind of like a modular infrastructure, right? That you may use all of it, or you may not use all of it. Is that how it works?
It's the most logical way of thinking of it, yes. So what you would do is say if you were going to design a water treatment plant from scratch, right? You'd look at what your risks are in terms of water quality in your catchment, to understand what you had to remove to meet your water quality objectives, right? And so if you've got, say, hard water, if you've got algal risk, if you've got some other types of risk like so manganese or iron or aluminium, or so metals, there's different processes that can remove those. There's things like linked to algae, you've got taste and odour causing compounds or algal toxins. So there's another set of processes that you would implement to remove that. So it's understanding what's in your raw water, what you need to remove those things in your raw water to meet your final water quality objectives.
Yeah, okay. And how do you know what's on your raw water? Like, because it looks like that's the key. Like, if I know how my raw water behaves, then I know which modules and which processes do I need. But how do I know that?
Good one. It's all around monitoring, right? So it's one of those things as well where, how long is a piece of string in terms of your monitoring program. It can be quite expensive to monitor for every single type of contaminant that's out there. Like some of your pathogen type groups, like your Cryptosporidium or Giardia, can be quite expensive for each test that you do in a lab. But there are a lot of available, especially these days. Technology is getting really great in terms of continuous sort of instrumentation that you can have sitting there that's kind of continually monitoring water quality. So you can get a really great picture of what your raw water quality is. So you can characterize, at the time when you get to that point, say, yep, we need to look at upgrading our water treatment plant. You can build that envelope, that water quality envelope, based on that historic data you've collected, to understand what you actually need to do as part of that upgrade design.
Yeah, okay. And then when you design the water treatment process, would you design for those changes as well? You mentioned an envelope, so I would imagine it's not designing for one particular set of conditions in the water, but make sure that the plant can respond to different things or different quality standards or quality conditions are coming through the raw water.
Exactly right. So it's tricky, especially with climate change and not having access to a crystal ball, understanding what you should be designing for. And this is one of my day-to-days, questions, issues. We typically design for, a worst-case scenario so that we make sure that, even under the worst case that we've historically seen, this plant will be able to supply safe, reliable drinking water to customers. But there's always the question of how bad can it get? Like, have we seen the worst of climate change? And that's a really difficult one to put a boundary around. So, we always like to have that sort of, for example, if the catchment we're looking at maybe hasn't seen a bushfire followed by a big rain event, we might like to throw in a bit of a hypothetical set of numbers just to make sure that if that did happen, because it is a real possibility, that plant would be able to meet those.
To that.
Yeah, exactly right.
So is that how basically you look into, that was one of my questions that I had, how do we prepare in climate change and with things that could happen in the future? So you come up with like different scenarios in terms, just like we work on the scenarios for temperature, for precipitation, then how would that affect your raw water conditions, so you can test those plants that you either have now or that you're designing for the future?
Yeah, so I mean, there's a lot of models out there. Someone once said to me that the only thing you know about a model is that it's always wrong. So it's a dark science, water quality modeling. It is like there are people who have developed models for raw water sources. And tried to implement what that might look like under various climate change scenarios. It is hard to, as I said, put boundaries around what you're actually going to do. So the way we approach it is developing or implementing flexibility into any designs that we do. And in the planning phase, we would typically develop an adaptive investment strategy. So looking at, what do we need to do now to address the current issues? But in the future, we want to leave open the ability to move to this type of process or this type of process, and what's the trigger for making that decision, and when is that trigger likely to happen? So, for example, for the last, decade, we've been talking about a reduction in the disinfection byproducts of the total trihalomethane targets for drinking water. We've been speculating what it might be, when it might come in. So we're kind of preparing for it, but we just don't know what it will be. So we don't know that if we, say, upgrade a treatment plant now to include a process that will meet the current disinfection byproduct limits, whether it will also meet the future disinfection byproduct limits. So what we're doing is we're saying, yep, we need to do this now. This is going to meet or mitigate our current risk. But between then, or now and then, whenever then is, we need to do some more work around trying to understand what the gap will be. Like, what will the performance of our new plant be? Could it meet XYZ limits if it needed to?
Yeah.
So that when that disinfection byproduct limit change comes in, we're prepared. We know what sort of path we want to take with our adaptive strategy.
Yeah. And how would that work for plants that are built already? Because, I mean, you would be involved in many things that are expansion or new plants or whatever, but what about the ones that are already there, or maybe they're even old, you know, and like, is there still a chance to kind of implement that adaptive kind of planning and those triggers to improve those at certain points in time?
Yep, most definitely. It applies for, not just starting from scratch plants, but most definitely upgrades, because that's essentially what we've got at Sydney Water is, I can't remember if it's nine drinking water plants. They're all existing, and what we do first is we do like a baseline. It's almost like a baseline. What have we got? What have we got? What's the capacity of that plant? What's the performance limitations of that plant under current conditions, under various scenarios of quality, raw water quality, like say this this bushfire followed by rain scenario, or a drought followed by rain scenario. So looking at what the current plant might do or be able to achieve under various scenarios, then understanding, I guess we also factor in growth, because that's also a big one at the minute. If these events happen, when will the plant no longer have the ability to treat that water? So it's not just quality, it's quantity as well. So often if you have poor water quality, you might be able to produce water of the right quality, but you have to run the plant at a lower rate. So you're getting less water. And there will be a point with growth that will not be sufficient to meet the demand. So it can be quite complex. I think I might have moved away from what your actual question was. But it does apply for new and existing plants. It's about being adaptable and flexible for climate, for growth, for whatever regulatory changes, whatever can potentially be thrown at you. So it's keeps you on your toes.
Yeah, absolutely. Because in some of the parts, like I'm a civil engineer, in some of the things is a little bit more definite. Not in water. Water always has that component of like what's going to happen in the future. I'm more on the part of the quantity, but the quality is just a whole other dimension. While other parts of engineering might be like your conditions for your design might be a lot more known, and yet you have all your security factors and all of that, but it's a lot more tangible and it's a lot more defined. But this one is from the get-go is like the quality can change in time, like now, and it can change in the future, and the volume. That was another question that I had, like when you have to change the conditions of your treatment and like maybe not running it at the optimal kind of combination of things, maybe the output is a lot less, and then that starts being important for the quantity. That's totally fine and totally right. I had a question. Is the water treatment process energy intensive? Like I know wastewater treatment is very energy intensive, but is it drinking water, like treatment for drinking purposes, also very energy intensive?
With your conventional processes, definitely nowhere near the scale of wastewater. Obviously in wastewater it's your aeration processes which are the killer. Say if you had a dissolved air flotation that I mentioned before, that may have the highest in terms of treatment processes, energy use. For drinking water, it's mainly pumping. It's mainly getting the water, say, out of the river into the plant. It's pumping it around the networks. That is the main use of power currently for drinking water schemes. However, we have been considering, I guess, not just power consumption, but looking at, your embedded greenhouse gas emissions, which are, because obviously not just Sydney Water, but most utilities have got some form of net zero target in the future. So we have to, build this kind of assessment into what we're doing. So looking forward, as I mentioned, around disinfection byproduct limits, some of the processes that we're considering is like, say, ozone, which is quite a big consumer of power. But the alternative to ozone is, say, an activated carbon process. And I mean, activated carbon itself has quite a lot of embedded carbon because it's made of carbon.
Yeah.
Mostly depends on the process that is used to, I guess, activate it to manufacture it. But these are the kind of processes that in the future, if we need them, we do need to take into account the embedded carbon or the non-embedded carbon.
Yeah, all the different greenhouse emissions,
exactly,
and all the scopes and everything. Yeah.
So we do incorporate, if we do consider, say, an ozone process, we will also include a solar farm potentially, or some way of
offsetting.
That's the word, offsetting that power consumption.
Yeah, no, that's great. I guess we have talked about this during this conversation, but what are the biggest challenges that are currently on water treatment? Is it around that climate change variability? Is it around technology? Is it all everything and all at the same time?
Pretty much biggest challenges. Yeah, I mean, it is definitely the climate change piece, in my opinion, and that lack of being psychic and knowing how bad it can potentially get. I mean, we can only plan for what we know. We can be flexible, but we've got to. There is, especially with drinking water, because we need water, right? We need water. We need safe water, and it has to be there when we turn on the tap. So it's a lot more risky if you get it wrong. We need to be flexible. We need to work together to get to the right answer. And I would say another challenge at the minute, and maybe this is something for the people that listen to this, is people. We need more people to get into water treatment and help out and come join us.
Yeah, that was one of my questions. Actually, I'll bring it forward. But what would be your message to young water professionals that might be listening to this?
If you love chemistry, water treatment is probably for you. And I mean, it's not like it's not just, I guess, metropolitan cities where where it is required. Water is required everywhere. It's clean drinking water is important for everyone in the world, and there's many people that don't have it. So I think having the skills around drinking water treatment are very transferable to other locations. It's feel good. You're doing something for the good of mankind.
Yeah, absolutely.
Yeah, and it's fun. It's interesting, right?
Yeah. One of the things I wanted to touch on was, like, you mentioned in your bio that one of your passions is also bringing people together. We have talked about young water professionals joining this, and then bringing people together to learn about water quality through storytelling and collaboration. Which is, I imagine, like the angle that you have from the Water Quality Specialist Network from AWA. Let me tell you first that that's one of the reasons that this project exists, is just to trying to get people together, like to learn about different areas of the industry. But from your experience, what would be the key to ensuring that storytelling really reaches like an audience, especially in topics like this that can get really technical, really into the nitty-gritty of the chemistry, of the microbiology, of even the quantity and quality of water? How do we reach to the audience when
Yeah.
it's so technical.
It's hard, isn't it? I mean, and I think you're doing a great job, because this is, I guess, a forum where it won't just be your water treatment nerds who are going to see it, right? But
Hopefully.
but I mean, I suppose for me, it's, you know, outside of work, it's really your backyard, your barbecue conversations, talking through, because there's a lot of I guess, mysteriousness around water. And as I said earlier, like, people turn on the tap, they don't know where that's come from. People flush their toilet, they don't know where that's going. It's being involved in some of that, in some of the community outreach work. I haven't myself done much for some years now, but I used to try to get involved with schools and sort of taking people through, like, water quality and where water comes from, and how do we make sure that it's clean. I mean, with the Water Quality Specialist Network with Australian Water Association, we try to present, each year in the last few years, we've had a panel at Ozwater. Obviously, Ozwater is the water industry, so you're kind of screaming into the void. It's people, they already know the stuff, right? But for me, it's also it's around sharing knowledge, and because I know you find little isolated groups, especially when we had COVID. Everyone was isolated, but there's people who face similar problems, and they don't know. Like, but if they could connect, then we could share the knowledge. Someone could, you don't have to start from scratch when you're trying to solve a problem because it's probably not new. So there's quite a lot of value I feel in sharing, I guess, case studies, having the conversation and collaborating. And I think the key is that storytelling piece. So doing it in an engaging way. And as you say, it's very, it's hard to, when you're a nerd, to not get technical, because you have to be aware of who your audience is, right? So you got to use the right words that don't just, people.
Yeah, I think it's like connecting it with a lot of the things that connect us to water all the time, and then kind of show them the light of, like, what is it that is behind all those processes. Oh, well, Sally, thank you very much. I have one more question that I'm asking everyone that I'm inviting here. Why do you work in the water industry?
I mean, aside from the fact that it's a job that's job for life, right? Everyone's always going to need water. It's it's critical to life. But I guess I did actually fall into it, to be honest. I did my honours year at Macquarie Uni, having no idea what I wanted to do, and sort of fell into a project that was genotyping cryptosporidium from kangaroos, of course. And from there, I managed to get a job in Sydney Water's crypto lab and just went from there. But yeah, honestly, I didn't go water, that's what I want to do. But yeah.
Yeah, I think that's normal, especially because we don't get a lot of exposure to it while we're studying. At least I didn't that much until I took like proper water courses and everything. But it's more about like in whatever way we got into, like what like we stayed. And I think what you say is about like what you say about saying water is needed all the time, and like but it could be a job for life. I think it is certainly the case because and it's so broad still that we can work from different angles, but it's definitely a resource that everyone needs, every part of society needs, and it's definitely very rewarding like to be working on this. Yeah. Well, Sally, thank you very much for your time today. You have shared so much knowledge, like from the basics and like all these processes and modules that can happen, and like all the challenges that water treatment processes have as well. Reflections around like storytelling and like about career-wise, we certainly know, or now I certainly understand a little bit more about water treatment. I'm not in this area at all, and it's certainly an essential part of the water sector. for everything that we want to do in the future. So yeah, very inspiring. Thank you very much for joining us.
No problem. Thank you for having me.
And well, to you, my friend, thank you very much for tuning in and listening to this episode of Our Water Connection. I hope you enjoyed the ride with Sally today. Follow us on LinkedIn as Our Water Connection, and in Twitter or X, or I don't know how to call it anymore, as Our Water Connect, to hear all the updates and new episodes coming. Until next time.